Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility.
जॉइन कला देखो हेलो गार्गी हैं लेफ्ट ही okay. Bhavesh, are you there?
Yes, sir. Yes,
Okay.
sir. I am here, sir.
Okay. So you can present now. Gargi will join later, right? Okay.
Okay, sir. Thank you, sir. I will
Right.
start.
Right, sir. Yeah.
Sir, I have shared my screen. Is it visible, sir?
Yeah, it is visible. It is visible.
Okay, sir.
So okay. Thank you so much for presenting the research paper here. Okay, you can start now. Thank you.
Okay, sir. Thank you, sir. Respected chairperson, sir. Respected research scholar. Myself, Bhavesh Das, Assistant Professor, Department of Mathematics, Arya Vidyapeeth College, Autonomous, Assam. The title of my paper is On Deficient Jumkiller Number. So it consists of abstract, introduction, and main results. So here is the abstract portion. So we have defined a new uh, generalized perfect number that is called Jumkiller number, and we presented some numerical result of this deficient Jumkiller number. So before going to discuss about deficient Jumkiller number, here we have written from where we have motivated to work on that number. So all of you know what is a classical perfect number. Uh, If n is a classical perfect number, then we can write sigma of n equal to twice n, where sigma of n is a sum of all positive divisors of n. So far, only 52 such classical perfect numbers are discovered. All the perfect numbers are even perfect number. There is no example of odd perfect number. Using the notion of classical perfect numbers, generalized perfect number has been developed in recent years. So Jumkeler numbers are also one of the generalized classical perfect number. A positive integer n is said to be a Jumkeler number if the positive divisors of n can be partitioned into two disjoint subset A and B such that theta of A equal to theta of B, where theta of D denotes the sum of all elements of the set D. For Jumkeler number n, we can write theta of A plus theta of B equal to sigma of n. So the idea of Jumkeller number was first introduced by Jumkeller in the year 2003. Some example of Jumkeller numbers are 6, 12, 20, 20, 28, 30, 40, etc. Another generalized Jumkeller numbers are unitary Jumkeller number. So a positive integer n is said to be a unitary Jumkeller number if the unitary positive divisors of n can be partitioned into two disjoint subset A and B such that theta of A equal to theta of B. So unitary divisors means if D is a unitary divisor of n, then GCD of D comma n by D equal to always 1. That means D and n by D are relatively prime. So these are some example of unitary Jumkeller number, 60, 30, 42, etc. So next we have introduced the deficient Jumkeller number. So this number also motivated from the definition of a Jumkeller number. We call a number is deficient Jumkeller number if all the divisors can be partition the set of all disjoint set A and B such that theta of A greater than theta of B, or theta of B strictly greater than theta of A. That is, also we can write theta of A plus D equal to theta of B, or theta of B plus D equal to theta of A holds, where D is theta of D denotes the sum of all elements in the set D, and D is a divisor such that D always lies between 1 and n. D may be 1. This divisor is called the deficient divisor of n. A deficient Jungkiller partition for a positive integer n is a partition a comma b of a set of positive divisors of n with deficient divisor d counted in the sum of deficient partition of a, say, such that sum of all elements in both a, including d in the sum of a, and b is equal to sigma of n plus d by 2. Deficient perfect numbers are solution of the functional equation sigma n equal to twice n minus d, where d is a deficient divisor of n. All deficient perfect numbers are deficient Jungkiller number. So if we take an example, suppose 130, consider a number 136. So 136 is a deficient Jungkiller number with deficient divisor 2. Since the partitions of divisors are, so we have a two partition A and B. So uh, A has the element 1, 2, 4, 8, 8, 17, 34, 68, and B has the only element 136. These are divisors of 136. If we sum up, that means theta of A, we can write 134. Theta of B, we can write 136. So therefore, we can write theta of A plus 2 equal to theta of B. Moreover, sigma of 136 by 2 equal to, we can also write 270 plus 2 by 2 equal to 136. So these are some example of deficient Jungkiller number: 10, 144, 14, 44, 136. We have obtained the following result for deficient Jungkiller number. Proposition 1. If n is a deficient Jungkiller number with divisor d, then sigma of n is even if and only if d is even, or sigma of n is odd if and only if d is odd number. Sigma of n plus d always greater than or equal to twice n, and if sigma of n equal to twice n minus d, then n is a deficient perfect number. That means deficient perfect numbers are deficient Jungkiller number. If n equal to 2 power of alpha, p1 alpha 1, p2 alpha 2 power of alpha 2 dot pr alpha r is the prime factorization of deficient Jungkiller number, then at least one of alpha I are even, and alpha must be 0 or alpha is a odd number. So this is a simple proof. Next, remark 2.1. If n is a deficient Jungkiller number with deficient partition a comma b of the set of positive divisors of n with deficient divisor d counted in the sum of b, then sigma of n always strictly less than twice of theta a. Proposition 2.2. If n is a deficient or deficient Jungkiller number with deficient divisor d, then n must be a perfect square. Proposition 2.3. An integer n is a deficient Jungkiller number with deficient divisor d if and only if sigma of n plus d by 2 minus n is a sum of distinct proper divisors of n. There is no proposition 2.4. There is no odd deficient Jungkiller number of the form n equal to p power of alpha. Uh, from the last proposition, we have obtained this remark. For alpha greater than or equal to 1, n equal to 2 power of alpha is the only deficient Jungkiller number of the form n equal to p power of alpha. Proposition 2.5. If 2 power of alpha plus 1 is a prime number, then n equal to 2 power of alpha minus 1 into 2 power of alpha plus 1 is a deficient Jungkiller number with deficient divisor 2, where alpha greater than or equal to 1. Proposition 2.6. If 2 power of alpha plus 3 is a prime number, then n equal to 2 power of alpha minus 1 into 2 power of alpha plus 3 is a deficient Jungkiller number with deficient divisor 2 or 4, where alpha greater than or equal to 1. Proposition 2.6, 2.7 also gives a form of deficient Jungkiller number with deficient divisor 2 or 4 or 8. Proposition 2.8. If p is a prime number and p is strictly less than alpha, and if 2 power of alpha plus mp is a prime number, then n equal to 2 power of alpha minus 1 into 2 power of alpha plus mp is a deficient Jungkiller number with deficient divisor less than or equal to 2 power of p, where mp equal to 2 power of p minus 1 is a Martian prime number. The prime number of the form 2 power of p minus 1 is called Martian prime number. These are some numerical examples. If we consider second Martian prime, first one is 2, second one is 3, then 14, 44, 152, 8384 are deficient Jumkelar number. If we consider third Martian prime number, 7, then 184, 2272, 33664 are deficient Jumkelar number. If we consider fifth Martian prime, M5 equal to fourth Martian prime 31, then 8452096 is a deficient Jumkelar number. If we consider M7 equal to 127, then 49024, 589312 are deficient Jumkelar number. We have the following result for deficient Jumkelar number of the form 2 part of alpha p. If n equal to 2 power of alpha, p is a deficient Jumkelar number with deficient divisor d equal to 2 power of m, where m less than equal to alpha, then 2 power of alpha plus 1 minus 1 greater than equal to always p minus d. So these are the results so far we have developed for deficient Jumkelar number, and these are the references we have taken. Thank you.
Hello.
Yes, sir.
Please show me your reference once again. Reference list.
References, sir.
Yeah.
Okay, sir. Is it feasible, sir?
Yeah, it is visible here. So you have mentioned there reference number 2, where it is written
Yes, sir.
unitary perfect numbers, right?
Yes,
So
sir.
that is a 1996. It is a paper in Canadian Mathematical Bulletin. So
Yes, sir.
what? Yeah, in your research paper, what things you have taken from this reference?
Yes, sir. We have a Jumkelar number. It is
Okay.
developed into. It was developed 2003.
Yeah.
Then from Jumkelar number, another number also developed, that is unitary Jumkelar number.
So
So for yes, sir. For
uh,
unitary Jumkelar number, so the definition of unitary divisor is taken from that paper, sir.
right. So please, I have not seen the definition of Jumkelan number. So can you show me again?
Yes, sir. Sure,
Yeah.
sir. So this is the definition of Jumkelar number. Suppose
Okay.
n is a suppose if we consider, sir, number 6,
Right.
then divisors are 1, 2, 3, and 6. And
Right.
if we consider set A containing the number 1, 2, 3, and if we sum up this number 1 plus 2 plus 8, that is equal to 6. And
Right.
another set we considering B having the element 6. So sum of the numbers of A equal to sum of the numbers of B. So this is the definition of Jumkelar number, sir.
Okay. So all are even number, or any kind of odd number is there in the Jumkelan number?
Yes, sir. There have a for Jumkelar number, there have a also odd number also.
Odd number also. So you have shown in the first some examples. All are even numbers. You see,
Yes.
6, 12, 20, 24.
Yes, sir.
Yeah, but
Yes, sir.
uh, after how many numbers the odd numbers are appeared actually?
Actually, sir, it is maybe 6 digit, maybe 7 digit of odd
Oh,
number.
the bigger number, right? Okay.
Yes,
So
sir.
have any kind of paper is there that there exist um, uh, perfect numbers in Jumkelan numbers? Have you any
Okay,
paper?
sir.
Hmm.
Sir, all perfect numbers are Jumkelar numbers, sir. Actually, the definition of Jumkelar, one can also say
Oh, all
those number
perfect.
which set is yes, sir, because theta A plus theta B equal to what? N.
It's okay.
Uh, uh,
All perfect numbers are Jumkelan numbers, but
yes, sir. Yes, sir.
is the converse is
All
true?
no, sir. No, always not two, sir. Because 12 is a Jumkelar number.
Huh.
It is not a perfect number.
Yeah. So that is an example. But all perfect numbers are Jumkelan number. No. Okay.
Yes, sir.
Right.
Yes, sir. Yes, sir. Yeah.
So any kind of format numbers that is appeared in there.
For deficient. So, sir, so we have some numbers
Yeah.
like so actually not close to that, sir. For example, 2 power of alpha plus 1.
Right. Right.
So it is a
Yeah.
prime number. We can say. Then we have also deficient number of this form, 2 power of alpha minus 1, 2 power of alpha plus 1. So it is,
Oh.
one can say it is associated with the Fermat prime number also. But the study is still going on, sir. It is just basic things we have developed so far.
Okay. It is a very newly developed number sequence. 2003.
Yes, sir.
No. Yeah. That's right.
Yes, sir. Yes, sir. Perfect. Jumkelar numbers developed in 2003, and
Sir,
using that definition, we also trying to develop the deficient Jumkelar numbers. Sir.
so just for curiosity, I want to tell some more questions to you, please. Uh,
Yes, sir.
uh, any kind of recurrence relations you have for Junkelar number?
Okay, sir. There have no recurrence numbers so far. I have
Recurrence
observed.
relation, recurrence relations I'm talking about. Like
Okay,
like
sir. No, sir.
like every
Yes,
number
sir. Actually,
sequence, every number sequence has a recurrence relation, right? In
yes, sir.
so any type of recurrence relation is in Junkelar number is there.
Okay, sir. Some special class of number there.
Hmm.
For example, if we consider a perfect number, then the all numbers are of the form 2 power of p minus 1 into 2 power of p minus 1.
Right.
So there have also certain form of numbers which are also Jumkelar number.
Okay. No, my question is something different. I am talking about any kind of recurrence relations exist in for this sequence or not?
Um, no, no, sir. No, no, no. No recurrence,
No.
recurrence relation for Jumkelar number.
Okay. That cannot be possible according to you. No?
Yes, sir.
No,
Not possible, sir.
okay. Thank you. Thank you so much. Thank you.
Thank you, sir. Thank you,
Okay.
sir.
Is my screen visible to everyone? Hello? Am I audible?
Yes, yes.
Good morning everyone. Thank you for giving me opportunity to giving the contributed talk in the National Seminar on Number Theory and Lie Algebra. Myself, Dr. Gargi Trivedi. I am Assistant Professor at Maharaja Sayaji Rao University, Applied Mathematics Department. Today I'll be talking about
So,
interdisciplinary
Dr.
application
Gargi,
of
Dr.
mathematics.
Gargi,
Yes, yes
sorry
sir.
for the interruption.
Yes, sir.
So please full screen your slides. It is not in the full screen mode, I think.
Yes, sir.
Okay. Yeah. Now it is in. No, not showing. You, yes. Yeah. Now it is. Ah, just use the key Control L.
Control
L.
L.
Otherwise, you have a screen as a concon. Huh? On the right corner, there is a symbol of two arrow mark symbol. I think maybe arrow mark na? Up down. Uh, before before setting, there is a symbol. You see before setting on the right hand side. On the right hand, move to right hand side, top right hand side. Your cursor is on the below, top, go to the top one, top. Yes, then come to right hand side, right side. There is a setting. After edit with Acrobat, there is a setting you see. Before setting, there is a symbol. Control L marla kahla. Before setting, there is a symbol you see. Edit with Acrobat, it is written there. Edit with Acrobat. See on the right hand side top. Edit with Acrobat. Edit with Acrobat. Before that, double arrow symbol is there. What's the title?
Let me try with PowerPoint presentation also. I also have there with me.
So this is PDF or what?
Now is it visible, sir?
Yes. Now it is in the full screen mode. Okay, you continue here.
Okay.
You continue.
Today I'm talking about the interdisciplinary application of mathematics from image fusion to real world problem solving. Mathematics is often to seen an abstract subject, but in reality it is a backbone of many real world applications, especially in the field of computer science and image processing. Let's dive into it. First, we'll see the introduction, then the proposed methodology of our problem, then analyze the algorithm's effectiveness, comparative analysis, and the conclusion. So, image fusion is the process of combining multiple images into the create single one, which is more informative. There are many type of image can be fused. Suppose multi-exposure fusion, different time span fusion. The same image is taken at the different time period. If we fuse that, we can get the more information from the single image. The medical image fusion and infrared MRI images give us the soft tissue data, SPECT images give us the anatomical data. If we fuse two images of MRI and SPECT, we can get both the data from the single images. Infrared and visible images, we can fuse to get the more informative image from the single images. The other type of image is the multifocus image fusion, back focused and front focus image fusion. If we fuse both the images, we can get the single image which is more sharper and having a more informative. We can introduce machine learning to this image fusion. Machine learning is used to analyze the data and pattern and increase the accuracy, automation, and adaptability. In our architecture, what we have done, we have inputted two type of different modality of images. Suppose MRI and CT images, which both have different images. One contain bone structure, one contains soft tissue structure. Then we apply partial differential equation pre-processing to these images, then extracted the feature using 4 techniques. Then we have normalized the technique. Then we pass these features to the to train for the training CNN and the fuse the images using PCA. This is the problem statement of our algorithm, that we aim to develop such an algorithm using PDA and machine learning to challenge the current limitations like noise, feature distortion, redundancy. Okay. And we want to enhance the quality of images for processing the multimodal and multifocus images. We will apply this algorithm in 3 application: medical images, multi-sensor images, and multifocus images, that which can be used in the field like computer vision, remote sensing, and robotics. To check the algorithm and to developing, we have used this hardware and software for our algorithm development. This is our algorithm structure, that we have inputted two type of distorted images. One is a front focus, other is a rear focus. Then apply the pre-processing of denoising, alignment and scaling for PD. Then the enhanced image will be capture four features from this four methods. And the normalization technique we have developed, that is robot z square normalization, and all these feature will pass to the CNN, and we will apply the automated pooling uh, to train the data. And after that, using the feed forward backward propagation method, we will finally get one fused image. These are the functioning of our novel algorithm, that no one has done a pre-processing by PDE so far. Then we have extracted feature from the PDE. The normalization technique we have developed so far new. The traditional z-score technique is using mean. We have used median for that. Then for the optimization, we have used CNN and use the feature by using PCA. For that fusion, we have used adaptive fusion, our developed rule for the fusion. This is the modified Paronomalic model for PD pre-processing we have used. These are some coefficient that control our amount of diffusion, direction, smoothness, AG for preserving the images. And then we have applied finite differentiation for image for approximate the image maximum intensity. These are the practical result that has been done here, that it is shown that the left hand side is very blur, but after applying our pre-processing, the right hand side is clearly visible. Here the back focus is not there, but after applying our algorithm, the window and the leaves are clearly visible. The experiment has been done in MATLAB to reduce noise and focus is the major features. Then after extracting this feature, we have applied this feature extraction technique: mean intensity, standard deviation, gradient magnitude and gradient orientation. And after that, we have applied the feature normalization technique uh, to normalize the feature. All these features has been seen that before normalization and after normalization, it is better. So no abnormalities or artifacts will be there before passing to the CNN. This is the feature distribution graph. Here we can see that the convergence, the loss convergence is decreasing after normalization technique. So loss is comparatively decreasing. Then all these features will be passed through CNN, and the relevant features will be extracted by using the back propagation method. In our work, we have introduced an innovative adaptation with convolutional layer and feature extraction layer. So to replace the non-linearity, we have used the zero by adding the linear anticipating the patterns to promote the accelerates the convergence. So our algorithm works faster than the traditional image fusion methods. Instead of traditional pooling, we have used automated pooling method. So our feature map will be generate fast, and adaptive filtering will be used to adjust the overfitting and dynamically adjust the criteria of features to input the data. First, we have used forward propagation for training, then loss computation, then again that from the loss propagation we have used back propagation layer by layer to compute the adjustment whatever the needed to minimize the loss function and gradually improve the performance. We have applied 15,000 images for training for different data set. Then we have optimized this algorithm, and iteration by iteration it will then it will make our model more realistic. This is the CNN architecture we have used in our paper. This is the adaptive learning rate. As we can see that the dropouts of the training are decreasing and loss is decreasing comparative to training loss and validating loss. This is the accuracy of a neurons. Then after these features, after extracting all the features from the both the images, we will fuse the images using PCA. For then we pre-process the data, compute principal component of each feature, and determine number of component, assign the weight automatically that we have learned from the back propagation, and finally we will get our fused image. These are the advantages of our model, that adaptive future normalization, convergence dynamics will be enhanced, and feature weighting by the PCA. We can use this model in medical as well as multispectral data, infrared images as well as multifocus images. This is a general model for all type of images that we can fuse. The limitation is it is a very sensitive to parameters. So while you choose the parameters, you need to very careful while tuning. Here we have checked the algorithms analysis and discussion. These are the experimental setup we have done while doing the training the algorithm. These are the data set we have used for the multifocus images, medical images as well as infrared and visible images. We have divided our data set into 70, 15 and 15. So for the training purpose, we have first pre-processed the data, train the model and performance evaluation. For image pre-processing, we have used PD, standardized data set for models accuracy, and for normalization, robust Z-server technique. This is the feature map for forward propagation. We have used MSC for loss calculation. This is a parameter while using training over epoch. These are the 50 epochs. Approximately it take 5 hours to train this model. This is the parameter updation after the backward propagation. So we got the parameter value upgraded after it. So this is the learning rate, optimization, algorithm parameters. Initially and after initially parameters have been optimized, and batch size impact, that after, whenever we take a higher batch size, we are getting more stable. So it can say that our algorithm is more faster. This is the feature weighting scheme that we have used for PCA. And to check the quality assessment of fusion result, we have used 3 quality checking matrices: SSIM, MI and Q factor. This is we have compare our method with discrete wavelet transformation, NSST, not subwave counter transformation. CBF and CNN are developed by other 2 users, and this is our developed algorithm. So we have compared this algorithm for all the data set we have taken. So at a conclusion, we can say that our method preserves more detail and better spatial consistency. So when you zoom the images, there is a if abnormality there, tumor is there in the brain image, our method can be find perfectly. Even it is in small amount, we can have a better visual perfection. So furthermore, we can evaluate these matrices for assessment of technique. We can use for subject quality assessment. We can use for this method for the surveillance purpose. Suppose um, we can say that the our if you take the images from the any embedded chip of security camera, there are so many multiple images from the security camera, you can get a single fuse image which is more informative rather than seeing the whole footage. These are the references that we have used. Thank you so much, Sambalpur University, the organization team, the technical team, chairperson of the this seminar, for giving me this opportunity. Thank you so much, everyone.
Thank you, Dr. Gargi, for presenting the paper and choosing this venue as your for these presentations. It's a very nice presentation. Uh, I
Thank
just I just want to ask some few questions. This just I want to know that you are
Yes,
doing a kind of image fusion, right?
yes, sir. Yes.
Okay. So can you differentiate? Man, actually, I don't understand. So there is a image blurring things also, blurring of
Yes.
images.
Yes,
So
sir.
any kind of difference between this fusing and blurring? So I am
Yes, sir.
confused.
Blurring is image pre-processed. We have seen that we have any image which is blurred, or it is not in high resolution. Okay. So if we
Okay.
pre-process the image, it will become good. But after
Okay.
pre-processing, if you zoom the data, if it is blur, you cannot find the details from it.
Right. Right.
But if you use this algorithm, so many blurs photos you have, and if you combine it, you can get a more perfect image, a single image.
Right. Right. And another thing I want to know the methodology
Yes,
you have applied in
yes,
your
sir.
algorithms that. So
Mm.
you have compared with some existing models, I think.
Yes, sir.
So what kind of existing models there? There are many transformations. I know something. I don't have many idea on that, but I know
Mm.
that there is an Arlon transformation. Have you heard this? Arnold.
Yes, sir. Arlon transformation, sir, it is used in signals, sir, not in images, sir.
Oh no, image blurring images that is also used, na?
Uh,
In blurring images that is
yes,
also
sir.
used in security purpose that is used. That is a
Uh,
good one, but there are other method also. Some chaotic methods are also there. I
uh,
forgot the name of that methods, but you have compared with which method actually? Which
Sir,
method?
I have you, sir. For the pre-processing, there are, as you say, there are so many methods. In that, we
Right.
have developed one model which is I have applied for patent also, Parona Malik model. We have
Okay.
modified that model for. We have developed new method for pre-processing. Obviously, you, as you are saying, there are so many methods are available.
Yeah.
Our idea is to fuse the images. So
Right.
to fuse the images, there are so many methods. Our traditional methods are available: NSCT, discrete wavelet transformation, PCA,
Right.
then CBF, if CNN. I have compared with 7 different techniques, sir.
Oh yes. Yes.
My model.
So
I have
what
used
is
machine learning for fusing, sir.
okay? So what is the time complexity of your algorithms here?
Actually, for limitation, training is very complicated. But
Okay.
after training, once you develop the model, it is faster than traditional methods, sir.
Nay, have you calculated the time complexity of your algorithms or your method other than
Yes, sir. I have, after development, it is fast, sir.
and first how can you show that the previous method what was the time complexity?
Uh,
So
as if I have shown in quality analysis, there is a faster in 2 3 seconds, faster than 2 3 seconds.
right no there is a time complexity like big O big O notation, I think big O n square big O n, so there are some kind of time complexities showing in that way. So have you calculated in that way or any just you have seen that
No,
there
no,
is a
sir. I have not calculated. I have
okay,
just applied the algorithm TikTok
right.
using.
Thank you once again, Dr. Gargi,
Thank you so much
for
for
the
the
presentation.
opportunity, sir.
Okay,
Thank you
thank
so
you.
much.
Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our Wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with LaTeX to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds
That included the numbers in the time of the Fibonacci sequence. Also, in this paper, we discuss the analytical continuation to the meromorphic function. And next, Raut and Panda sir also introduced the balancing zeta function, that is including the Riemann zeta function, including the balancing member. Also, it is present commoners consider the Lucas zeta function, that is a generalization form of the number sequence. Then, what is K generalized Pell sequence? If a Pell sequence we generalize in the nth term, these are the Pnk is equal to 2 Pn minus 1 plus Pn minus 2 up to Pn minus k. That is the generalized Pell sequence where the previously all term like 0, k minus 2, k minus 3, and so on, all are the initials are 0 and P1k is equal to 1. If we take the value of k is equal to 2, it is converted, the generalized Pell sequence is converted to the Pell sequence. This is the characteristic polynomial of the k generalized Pell number. That is x to the power k minus 2x k minus 1 and minus x minus 1. And this is the binet formula of the generalized Pell sequence. This is the Then we introduce the k generalized Pell zeta function. If I put the k generalization number, the sequence in the zeta function, it is converted to the k generalized Pell zeta function. This is the k generalized Pell zeta function. The zeta of Pell function is equal to summation n 1 to infinity 1 upon Pns. This also the boundary is the real of a complex number is greater than 0 in the term of real number. Aim of this work is to study the analytical continuation, and to compute its singularities, and find its residue at a simple pole, and we derive some special value at the negative integers. Analytical continuation. If we show analytical continuation, then previously we showing the series, the infinite series must be absolutely convergent at the half of the plan by real part of the complex number. These are some my proofs. These are the big proofs, that's why I am showing only the main result here. This is the finding the pole in a possible simple pole where it is meromorphic. The k generalized Pell zeta function can be meromorphically continued to whole complex plane with a simple pole. This also a proof. Then the simple pole, using the Binet formula, we can find this. This is the simple pole format. These are the small proof getting to take 0, and we find the poles. When I take k is equal to 2 and the two roots of the Pell functions, and we get the list of the poles, we put the value of n 1, 2, 3, and so on, we get the simple list of the simple poles here. This is also a remark to find the simple pole when k is even or k is odd. Then next find the residues at a simple pool. When our simple pool is S, then what is the residue? This is the formula of residue. This is also a proof, a long proof. Then only mention here the results. Then we discuss the value at negative integer. When we put the value of positive integer, we get some irrational. But when we take the negative integer in the place of the value, we get the number that belongs to rational number. I write some the proofs here. These proofs taken from the previous theorem that we also proved. This take from the previous theorem. This is the main proofs. This when we take the coefficient of the term that present in the meromorphic function, then the negative value of this function is belongs to a rational number. This is my conclusion. We study the arithmetic nature of special value in case generalized algebra functions in positive even integer. If you take the positive integer, then we get some values. But if we take if we take the negative integers, then we give some values. If we take the positive integer, then the values are the positive at a positive integer. It may be differ or it may be irrational number. So it is somewhat difficult to exactly exactly find the pattern of the value. So it is also a challenge to find the value at positive even integers. These are my reference. Thank you.
Thank you for your presentation. Any question from audience? If there is no question, let's clap for the speaker.
Thank you, everyone. Thank you.
Thank you. Thank you.
Online
Similarly, the different multiplication of three base like one is repeated L times, A2 is repeated M times, and A3 is repeated K times. And we can express these three combination of their digits as these three sums. Yeah. So these authors in 2021 found all Fibonacci numbers which are concatenation of two rep digits, and they proved that 13, 21, and up to 377. These are the only Fibonacci numbers which are concatenation of two rep digits. And Edovan and Kesky in 2021 found all Lucas numbers which are concatenation of two rep digits. And they proved that these are the only Lucas numbers which are concatenation of two rep digits. So what we'll do is we'll find all Padovan numbers which are concatenation of three base P rep digits, where this C1 is repeated L times, C2 is repeated M times, and C3 is repeated K times. So by doing some manipulations, we'll get this final expression, this sum. So here is the sequence of Padovan numbers, and here is the sequence of all sum of three base P rep digits. So we will intersect these two sequences. So to do this, our tools teach the linear forms in regarding Becker's theory and some reduction methods. So Becker's theory is so linear forms in logarithm is the expression beta 1 log alpha 1 plus beta 2 log alpha 2 plus beta n log alpha n, where all alpha and beta denotes the complex algebraic numbers. Yeah. So if beta is an algebraic number, then we take the minimal polynomial this f of x. Then we define the logarithmic height h of beta to be 1 by d log of the log of a naught leading term coefficient plus summation this term. And these are some properties of the logarithmic height which we need to calculate the heights of the algebraic numbers. So this is the matrix theorems which will, with the help of this, we'll found an upper bound for our variables in the main equations. So this is that if gamma is the form of ei power product vi power vi minus 1, and if this gamma is non-zero, then we'll get this lower bound for the absolute value of this log, for the log of the absolute value of this gamma. This is the lower bound for log absolute value of gamma. So which will provide an upper bound for our main variables. And this is the reduction techniques we have used to reduce the upper bounds. Yeah. So our main method is this equation is finitely many solutions, and this n is bounded by this term 1.8 times 10 power 47 log p power 7. And if we put p equals to 10, we'll get all the Padovan numbers which are concatenation of these 10 rep digits. So these are the rep digits. These are the Padovan numbers which can be expressed as the sum of 3 base p rep digits. 114, 151, 200, like this. Yeah, so for outlines of the proof here, this is the Pn term. So here we have used the Binet formula, and this is the right hand side sum of 3 base p rep digits. So first what we will do is we will write this equation in 3 different ways, and we will do some manipulations here to get these three upper bounds. This sum. So here you can see the inner part of this modulus and in the form of gamma. So here we apply the matrix theorems to get the upper bounds for this L, M, and N. So these are the bounds we have obtained for L log B, N log B, and N. So but these bounds are large, so we need to reduce this. So to reduce these bounds, we use Becker divided by reduction methods. Yeah. So how we have found this one? I'll give for particularly this example 9. For this equation 9, I'll give. So okay, this is the first power line equation. So we'll write this equation as this one. So taking absolute value on this side, we'll get this. Then dividing both sides by C1 p power log b power l plus n plus k, we'll get this bound 3 by b power l minus 1. So here you can see this is the gamma 1, where I'll take them eta 1 equals to p minus 1 c alpha by c1, eta 2 is alpha, eta 3 and b. So all these eta 1, eta 2 vector algebraic numbers, and b1 and b2 are positive integers. So next we'll calculate the heights of this eta 1, eta 2, eta 3 using that logarithmic height formula. So h of this eta 1 is less than a whole log 3, h of the alpha is log alpha by 3, and h of beta is log 3. So now we find the heights. Next we'll find a1, a2 and a3, which these symbols are in the matrix theorems. So after that we will apply the matrix theorems and we will find log absolute value of gamma 1 greater than this times this one. So we'll get L log P less than this quantity. Similarly, we'll get for next two terms like M log B and N. Yeah, this is L log B. Now for B equals to 10, if we will take a particular B value 10, then we'll round the bound N to be 6.2 10 power 49. But this is too large, so we need to reduce that with the help of backward reduction method. So after these are some expressions in the reduction methods. So after reducing the bounds, we get F, M, and these are the bounds like 86, 86, and 66, and 669. N is bounded by 669. So next we got the reduced bound N. So after that, we'll write a program in Mathematica and we'll find all the solutions. Yeah. Thank you. Any questions? Sir? Okay. Sir. Yes, sir. These are the sum of three base P averages. We can express these terms. Yes, sir. Yes, sir. Alpha is the dominant root here. No, sir. That condition is not present will be difficult because we have taken all sequences. Like we are taking all the problems like where we are getting at least one dominant root. So here alpha is dominant root and we can come on roots complex conjugate roots. Yes. Yes, sir. We can also generalize to sum of k replicates. Yes, sir. So sum of k replicates. Sir? Actually, what base three base with averages, we found these explicit solutions for so for k replicates. That's why I have not tried, but yes, sir. Same calculation, same process, but we will apply 4 times the matrix theorem and 4 times the reduction matrix. Here 3 terms are there, so we are applying 3 times matrix theorems and 3 times reduction matrix. So if we add 4 times, then 4 the averages, then there will be 4 times. So it will be more. So if we do k times the averages, so again we have to apply for k times the matrix theorems.
Mass at DD University. DD University. Third in. Good morning, everyone. I am Industry Veda, Research Scholar of Sambalpur University, under the supervision of Professor Prasad Kamaraya. So, my topic is multiplicative dependency on higher order organization having piecewise polynomial.
Different type of zeta function like Khare zeta function and Loy zeta function, and this can be obtained from the work of Castles and Lorentz. And also it is helps in finding primitive divisors in different occurrence sequences. And this can be understood by this. Graphical primitive divisors say that after 13 number of terms, all the terms is a primitive divisor. And suppose you want to find multiplicative dependence between two Fibonacci numbers, means we have to solve this type of equation. Here the variable is n and x and y. So to solve this Raphael equation, we can observe that the Fn and Mn should have the same set of time divisors. But graphical primitive divisors say that after 30 number of term, no term has every term has a primitive divisors. Means after 30 number of term, any two Fibonacci are multiplicative independent. These multiplicative dependence and primitive divisors are interrelated, and they are related. Means if more is the primitive divisor, less is the multiplicative dependency, and more is the multiplicative dependence means less is the primitive divisors in that case. So this application motivates different researchers to search the multiplicative dependency in different higher recurrence sequences. For example, Luca and Zegler find out the multiplicative dependence K tuples coordinate from same binary recurrence sequence. And for that, they solve this Raphael equation. And in this Raphael equation, U and I are from the same binary recurrence sequences, and the exponent xi and they keep fixed, and solve this Raphael equation and found that there are only finitely many multiplicative dependence K tuples. Gomez and Luca generalize this this, and instead of taking binary recurrence, same binary recurrence sequences, they consider different binary recurrence sequences. And the binary recurrence sequence that we consider, they have only the real roots. And here they solve the same Diffie equation with u and I from the different binary recurrence sequences, and they xi and k, they make them variable and solve this Diffie equation and found that there are only finitely many solutions to this Diffie equation. But for general cases, for higher order recurrence sequences, no such general result has been found yet. But for some special cases, it has been found. Like Gomez and Luca find the multiplicative dependent strip pools with coordinate from Fibonacci number, which is higher order recurrence sequences, and also they find the multiplicative dependence pairs with both coordinates from K generalized Fibonacci sequence. And Gomez and its co-author find the multiplicative dependence pairs with one coordinate from K generalized Fibonacci sequence and another coordinate from K generalized Lucan sequence. And in all these cases, they found that there are only finitely many solutions. So, motivated by these researchers, we search the multiplicative dependence state with coordinates from higher order recurrences. And for that, we consider these higher order recurrences, where for n equal to 0, it gives value 1, and for n less than 0, it gives 0, and for n greater than or equal to 1, they satisfy this recurrence relation. With the coefficient of the recurrence relation either satisfy this condition or this condition. In both these conditions, C1i is greater than equal to 4. So the characteristic polynomials of this recurrence sequence is given by this, and Hanusa and its co-author find the Binet formula for this recurrence sequence. They found that the Binet formula is this, where alpha is the root of this characteristic polynomial, and the coefficient that is associated with the root is given by this. So we investigate this multiplicative dependence K tuples under certain condition. The first condition will take that if we try to find the multiplicative dependence K tuples, mean any K minus 1 of them are multiplicative independent. We take this condition because if K minus 1 is multiplicative dependent, then any superset of it is also multiplicative dependent. So there is nothing to search. That's why we consider that any K minus 1 of them is multiplicative independent. And we consider the exponent of the multiplicative relation should be equal to 1. And we consider this relation because if x1 of xn satisfy the multiplicative relation, then any integral multiple also satisfy that relation. So in this case also we get many solutions. So to reduce it, we take this condition. And the third condition is we take because in the flow we come up with the linear form sin laga देते, and to apply the matrix linear form sin laga देते, non-zeroness of that linear form is required, and for that condition we take this condition. So under this condition we investigate multiplicative dependence tuples, and in our case also we get finitely many solutions. So first we study the properties of recurrence sequence that we consider. And we found that the characteristic polynomial is a Picard polynomial, and which is get from the work of Heron and Yu and its co-author. And we found that under this condition, the dominant root, which is lies outside the unit circle, is lies between C1i and C1i plus 1. And also we find that the coefficient which is associated with the dominant root in the Binet-like formula, we found the bound for this, and we found that it is lies between half and 3/2. If you consider E and I as an error in the approximation in the first term of the Binet-like formula, then we found that the error also satisfies the same recurrence relation that the U and I satisfy. And for n is very large, the error term is going to 0 actually. Because this can be obtained as this Picard polynomial. Picard polynomial means only one root lies outside the unit circle and all the roots lies inside the unit circle. So as all the roots except the first root lies out inside the unit circle, so this term equal to 0. And from this relation we get that the error term tending to 0 when n tending to infinity. Also we found that the recurrence relation can be approximated using the given that formula, and we found that is equal to the rounded up to this number. This is the height of an algebraic number. Suppose you were given any algebraic number gamma, then its height is given by this relation. And if gamma is a rational number, then the definition reduces to this. That is log of maximum of P and Q. This is the properties of some height function. And by using this, we calculate the height of the dominant root, and we found that the height of the dominant root is less than log of I, and the height of CGI is log CGI because it's a rational number, and height of the coefficient that is associated with the dominant root is this one. And after studying the properties, we come to our main result. Here we find out multiplication tuples, and here we consider suppose UM1 up to UM10 multiplicative dependent. Any one of them are multiplicative independent. Then if you consider M is the base, all the MI, then this M is equal to this quantity. L is the maximum of C1I plus 2, and this is so that there are unlimited couples of presence. And also we find the bound for the exponent of the multiplication relation, and we found that the bound for the exponent of the multiplication is bounded by this relation. So this paper is published in International Journal of Number Theory. They are variable. If K is variable, Y is variable, we can also consider K is any variable also. Means if you fix K equal to 2, then you can work here K and K equal to suppose 1,000, then also we can work. So we can say that K is variable, Y is also variable.
Here, what is the condition of this UM differential?
And this one independent. Only that condition. UMI should be only that I consider. It is auto from this. So this should be commonly this type of. Means the coefficient satisfy either this condition or this condition, and the final coefficient should be equal to.
If you remove this condition, is there difficulty?
Yes. Under this condition, only the statistical element is Pisat polynomial, and the Pisat polynomial help us to calculate all the conditions.
What is the benefit of using research?
The importance of Pisat polynomial is that we can approximate the evidence sequence only using the first term of the Binet formula. So in first term of the Binet formula, we can approximate it. So it helps us to calculate it. All other terms.
Conditions are on coefficients, so this is very restrictive conditions. If you avoid these conditions, then it will be again
Sir, under this condition,
I am saying that if you try to remove the conditions on these coefficients on recurrence relation,
so it
another way, alternative way to use the research.
Other conditions. If other conditions are not given,
Recently, Hydus have published one, and they have taken this paper as reference. We check. They have published, they have proved that the density of this number of percent. This is arcade paper.
This is arcade, not it.
Also try to remove this condition.
Saying that, so try to remove this.
Is there any special example on this condition?
no special example. But no example.
one example is following is capable where it is good. That's the point.
Good job. Thank you so much. Next speaker is contributed talk, the last contributed talk before the invited talk. He is Ashtadhara Suna. He is also from Sambalpur University, but now he is in Sambalpur assistant professor Sambalpur. Still a student of Sambalpur.
Under the able guidance of Professor Prasanta Kumar Rai. Also working as an assistant in the Department of Mathematics, Government University, Sambalpur. So today I'm going to talk about our study on Pell polynomials of two variables. So as we all know that Pell numbers are linear recurring sequences, satisfying its linear recurrence, Pn equals to twice of Pn minus 1 plus Pn minus 2. So this motivation comes from the well-known Fibonacci numbers. So Pell numbers satisfy first few terms of Pell numbers are this, and Pell numbers satisfy this Binet formula that is given by that, where 1 plus root 2 and 1 minus root 2 are the roots of the characteristic polynomial of Pell numbers. The matrix representation of Pell numbers is given by this form. So many of the well-known identities like Catalan's identity, Versda's identity, many identities can be solved using this representation of Pell numbers. The associated Pell numbers that is associated with Pell numbers is also defined with the same relation, but with different initial condition, that is Q0 equals to 1 and Q1 equals to 3. It also has the same Binet form that is different from the Pell numbers. And the matrix representation of Lucas numbers is quite different from that of Pell numbers. So as we are working on Pell polynomials, so the motivation that we derive is from the Pell polynomials is defined using one variable which has a translation that is similar to that of Pell numbers, but with an extra x over here. instead of twice of Pn minus 1, we are having twice of x times Pn minus 1. With the same initial condition P0 of x equals to 0 and P1 of x equals to 1. I forgot to tell why Bell numbers are very interesting for us. So the Bell numbers that we are actually seeing here, these are actually derived from Bell's equation. But if you ask me who was Bell, John Bell was mathematician from England, but he has nothing to do with actually Bell's equation. I think if I'm not wrong, Leonard Euler attributed it to him about Bell's equation, but Bell's equation was long before done by Brahmagupta. Okay, so the associated Bell polynomials is also defined like this. So what we are actually doing is so some of the properties of polynomials are given like this. The generating function of polynomials are given like this. Functions. Okay. So the motivation that we are deriving is from that of Hermite polynomials. Hermite polynomials are very much interesting and are also very important to mathematics, and in particular they are very useful in studying partial differential equations. So in a way we are actually merging partial differential equations with number theory. So there are three types of Hermite polynomials: HEN, HN. These two are actually Hermite polynomials of one variable. This is Hermite polynomial. This can be generalized to Hermite polynomials of two variables. Okay, so they are related to each other by this relation, that is Hn of x 1 by 2 is same as Hen of x, and Hn 2x minus 1 is equal to Hn of x. So these are some of the properties. That is Hn x0 is equal to x to the power n. If you take y to be equal to 0, then you get Hn x 0 equals to x to the power n. And here if you see a term is given here, exponential of y dou square by dou x square applied on x. So this is something that is not that much conventional in conventional mathematics, but it actually came from a newer branch of mathematics called umbral calculus. Umbral calculus became very much famous from 19th century. So umbral calculus, what does umbral calculus actually does is it creates integral operator as well as differential operator, not as operators but as algebraic. It actually does calculations of integral and differential operators and find some of the interesting properties. Like you can do binomial theorem, that is x plus y to the power n as we all know as binomial expansion. So similar way you can actually find the binomial expansion of different types of operators. So in the reference I reference two of the books that I actually prefer studying umbral calculus. So if I can have chalk, yeah, this can be actually done. Expression of xy is equal to exponential of y dou square by dou x square x to the power x. So if you apply this operator to the power n, then you will get Hn of xy. And Hermite polynomials of two variables satisfy this differential equation, that is dou square by dou x square Hn of xy is same as dou by dou y of Hn xy. Also it has this very interesting property, that is dou by dou x of Hn xy is equal to n multiplied with Hn minus 1 and x plus twice of y dou by dou x applied of Hn is equal to Hn plus 1. So these type of properties are actually called monopolarity properties of polynomials. And also if you talk about the recurrence relation that is satisfied by Hermite polynomials of two variables, it is given by Hn plus 1 xy equals to. So if you directly see here, the coefficient is not constant here. Here n is actually varying. Okay. So how are Bell polynomials related to Hermite polynomials of two variables? They are related to Hermite polynomials of two variables by this relation. This is actually an integral representation of Bell polynomials as well as polynomials. So what we are actually doing is we are trying to generalize this Bell polynomials with an extra variable. So we are defining 12 polynomials of first kind by this relation and 12 polynomials of second kind by this relation. Okay. So if you see here, sorry. Yeah. So with an extra y to the power k, we are defining 12 polynomials of first kind, and in the Bell Lucas polynomials with an extra y to the power k, we are defining 12 polynomials of second kind. So with a bit of algebraic manipulation, we can show that the integral representation of Bell polynomials of first kind is given by this relation, whereas the integral representation of Bell polynomials of second kind has this integral representation. So basically, if you see recurrence sequences or recurrence polynomials, they are actually defined using the recurrence relation, and later actually the integral representations are found. But in our work, what we are actually doing is we are defining it using a summation formula, then we are finding the integral representation of it using Hermite polynomials, and finally we find the recurrence relation of Bell polynomials of first kind as well as Bell polynomials of second kind. So before going towards this, first we should note that in the integral representation we are actually not having hn of xy. Instead we are having hn 2xy. So we need to carefully work on this. Instead of x, actually we are having 2x here. So this will make a bit of difference. So we are countering the difference using this relation, that is hn 2x